Bridges are the unsung heroes of our transportation systems, silently bearing the weight of countless vehicles every day. Yet these structures are constantly subjected to a hidden threat: fatigue. Like a metal paperclip bent back and forth until it snaps, concrete too can weaken and eventually fail under repeated stress, a phenomenon known as fatigue. Understanding the fatigue properties of concrete is not just an academic exercise, it's crucial for ensuring the safety and longevity of our bridges. Fatigue in concrete bridges is a gradual process, often invisible to the naked eye. Tiny cracks, initiated by repeated loading and unloading, can propagate over time, compromising the structural integrity of the bridge. The consequences of ignoring fatigue can be catastrophic, leading to sudden and unexpected failures. Therefore, engineers and researchers are constantly striving to understand the mechanisms of fatigue and develop strategies to mitigate its effects. By studying fatigue properties, we can design bridges that are not only strong but also resilient, capable of withstanding the test of time and traffic. One of the most widely used methods for evaluating the fatigue behavior of concrete is the 4-point bending fatigue test. This test simulates the real-world loading conditions experienced by bridge decks. Imagine a concrete beam supported at 2 points near its ends, with 2 other points located symmetrically between the supports applying downward force. This arrangement creates a zone of constant bending moment in the central portion of the beam, mimicking the stresses experienced by a bridge deck under vehicular traffic. During the test, the concrete beam is subjected to cyclic loading, meaning the load is applied and removed repeatedly, simulating the passage of vehicles over a bridge. This cyclic loading allows researchers to observe how the concrete responds to repeated stress and identify the point at which fatigue cracks initiate and propagate. By varying the magnitude and frequency of the applied load, engineers can gather valuable data on the fatigue life of concrete under different stress conditions. The 4-point bending test, therefore, serves as a powerful tool for understanding the fatigue behavior of concrete and informing the design of durable and resilient bridge structures. Data obtained from the 4-point bending fatigue test is often represented graphically using SN curves. These curves plot the stress amplitude, S, against the number of cycles to failure, N. The SN curve provides a visual representation of the relationship between the applied stress level and the fatigue life of the concrete. However, predicting fatigue life with absolute certainty is a complex task due to the inherent variability in concrete properties. To account for this variability, engineers turn to statistical tools like the 2-parameter Weibull distribution. This distribution is commonly used to model the probability of failure in materials under cyclic loading. By fitting the Weibull distribution to experimental data, engineers can estimate the probability of a concrete structure surviving a certain number of loading cycles under a given stress level. This information is invaluable for assessing the long-term performance and reliability of concrete bridges and making informed decisions regarding their maintenance and rehabilitation. The insights gained from fatigue tests and statistical analyses have profound implications for the design and maintenance of concrete bridge decks. One crucial finding is the significant influence of the maximum stress level, SMAX, and the stress ratio, R, on fatigue life. SMAX represents the highest stress experienced by the concrete during each loading cycle, while R is the ratio of the minimum stress to the maximum stress. Higher SMAX values and lower R values generally lead to shorter fatigue lives. Another important consideration is the role of steel reinforcement. Concrete, while strong under compression, is inherently weak in tension. Steel reinforcement bars embedded within the concrete help to counteract these tensile stresses, enhancing the fatigue resistance of the bridge deck. By strategically placing and designing the reinforcement, engineers can effectively control crack propagation and extend the service life of concrete bridges. Understanding these factors allows for the development of more accurate fatigue design guidelines, the implementation of effective inspection and monitoring programs, and the timely repair or rehabilitation of aging bridges, ultimately contributing to a safer and more sustainable transportation infrastructure.